Well, let's just jump right in. So I want to talk today about some successes and challenges and also some failures that we've had in developing operando experiments for transient studies. And first, I definitely want to acknowledge the people that have helped me get these results that you'll see today. So Jason Malizia, he's a staff scientist at Idaho National Lab. He is the one that collected the data, and analyzed the data, and he enabled us to take spectroscopy sort of, what I'll say, outside of the box, right? A lot of people that do operando spectroscopy are using conventional commercial off-the-shelf systems, and Jason really helped us build our own system and make it work. And then, of course, Jim Pittman, I've been working with him for more than 20 years, building TAP systems. He helped us actually build the device and keep it working. He keeps all of the TAP systems working regularly. And Shane Palmer and Stephen Christie collected and analyzed some of the data. And then I need to recognize, of course, our industrial partners, Clariant Corporation, who have provided their expertise and the catalyst that we're going to talk about today. And then, of course, my mentors, Gregory Yablonsky and John Gleaves, who have been the founders of the TAP and transient kinetic approach to catalysis for many, many years. And then finally, I do want to also recognize our funding agency, the U.S. Department of Energy, that paid for this work and made this all possible. So the catalyst, can everyone hear me okay in the background? Or volume's okay? Good. The catalyst that I want to talk about today is chromium on alumina, and it's used in the CATOFIN process for propylene production. This is actually a really interesting industrial process. It's done in an adiabatic fixed bed reactor. So the propylene dehydrogenation is, of course, endothermic. And this is done, the way that the CATOFIN process is done, it's done with rapid short timescale switching between oxidizing and reducing conditions on the scale of minutes. And so what happens is first propane comes in, and you have the dehydrogenation. It's endothermic. The catalyst cools. The reactor cools down very quickly, and then the process turns around, and oxygen is injected, and it burns the carbon that's accumulated off of the surface, and then that exotherm helps heat the reaction back up and start the process all over again. So in the oxidized state, there's a nice green color to the catalyst, and then it pretty quickly collects and accumulates carbon. And this process happens hundreds of thousands of times over the 6-year life of the catalyst. So it's pretty interesting too. It's actually the reactors, it doesn't have the high aspect ratio like we typically think about in chemical engineering. It's a really wide bed system. So now, of course, the first thing that we do when we are going to look at a catalyst is we're going to characterize it ex situ, and that's shown here. This is just the UV-vis diffuse reflectance. So the black trace, I've got the catalyst that's in an oxidized state, and there's 2 peaks around 460 and 600 nanometers, and I'm calling them peaks, but they're, of course, negative going peaks here because I'm looking at the reflection. And so those reflections are associated with the chromia 3+. And then in the near IR, we also have a signal that's associated with the chromia oscillators. So the next thing I'm going to do is I'm going to take the catalyst, heat it up, get it hot, flow hydrogen over it, and reduce it. And then I'm going to cool it back down and take another spectrum. And that's what we see here. There's not a lot of change. The population of the chromia centers has increased, so the reflection has gone up. And there's definitely a big increase in the IR as well. So that's typical for catalysis. But what we really want to understand is, what does the catalyst look like when it's hot and there's gases flowing over it and it's actually doing the chemistry? And that, of course, is the realm of operando spectroscopy. Now, catalytic reactions, we typically study them from the gas phase, but operando spectroscopy enables us to directly observe the catalyst and as it's changing during the reaction. And what we want to be able to do is correlate those observed structures to the function that we see. But operando spectroscopy can be very challenging when we try to do transient experiments. It works great for steady state. But again, we want to understand, especially for the cataphin process, if things are hot, gases are flowing, and then we're switching between these oxidizing and reducing conditions. So the first thing that I want to show here is what happens when we just heat the catalyst up. And so the data that I showed before, the green trace there, that's the signal at room temperature, looks very much the same. I start heating it up and a couple of things happen. Well, first, these chromia 3+ transitions, they redshift, and then they broaden, and then they also decrease in intensity upon heating. And so looking at the full spectrum is kind of a lot, and so over on the right here, I've just pulled out different regions of interest where the chromia 3 transitions are, and we can follow how those different transitions change with temperature, and they all change a little bit differently. And then certainly in the IR, we can see past about 400 degrees C, that IR signal really picks up. And that's because we've got black body radiation, because now the catalyst is glowing red hot. So these temperature effects are going to be very important because remember, in the cataphin process, we're cycling between oxidizing and reducing conditions. So this, we'll come back to this in a little bit. Now, in operando spectroscopy, the way we started is where most people start. A lot of people have a device similar to this. You can buy this commercially. And so in these experiments, I want to study this transition between oxidizing and reducing conditions. And so I've got the catalyst, 50 milligrams of catalyst in the reactor. I start flowing gases. It's at reaction temperature. And so the catalyst is, maybe I'm flowing an inert gas, and then I'm going to switch on the hydrogen, and I'm going to reduce my oxidized catalyst. And that's what's shown in the bottom left here. And unfortunately, what happens is all of the change is over in about a minute's time. And if you look in the center here, now I've just pulled out the transitions that are interesting to me, associated with the chromia 3 oscillators. And what happens is almost instantaneously we reduce the catalyst, right? So we're going from chromia 6+ to 3+, and that we see that increase in reflection. And I can't really learn a lot from a step change like this. I really want to understand how things play out. And on this time scale, the transition is just too fast. Now, the other challenge, too, is if you look over on the right, now I've got the gas phase measurement. When I switch the hydrogen off and I just have the inert gas flowing, it takes quite a bit of time for the inert gas and then also the reacting gas to exit the reactor. Actually, much, much longer than in the transitions that we see when we switched on. So the problem here when doing transients in the operando, is that we don't have the gas phase and the spectroscopic information on the same time scale. That's what we want to address here. And one other thing I'll mention too is when you're flowing gases and you're switching, you get a lot of you can have a lot of effects from thermal effects from the gas switch, changing the gas density as well. And that's actually what is observed here. In the center, we have this little, this is the IR signal, we have this little dip in the signal, and that's because of the thermal effects of just switching the gas. And so that can obscure what's happening kinetically as well. Okay, so when we set out to do this, we want to be able to correlate the spectral change and the kinetic change in these transient experiments. And so what we need is, this I'll call it spectrokinetic device. We need well-defined transport because we want to understand what are the effects of the transient that are just transport and what are the effects that are the catalyst itself. We also want to be able to do very precise titrations and incrementally be able to probe the kinetic state of the catalyst, but then also see how it evolves as we make very precise changes to the kinetic state. And then, of course, for any kinetic measurement, it's required that we can do this isothermally. So it turns out that those first three things are, in fact, the design principles that TAP is based upon. And so when we built the spectrokinetic reactor, it is very much based on the TAP, or the temporal analysis of products technique that I've been working with throughout my career. But before I get into that exactly, I want to kind of back up and talk about transient methods and pulse response methods in particular. So what I'm showing here is not a tap experiment. This is just a pulse into into a carrier gas. So we have an advecting device. So we have complex transport, which is shown in the top right. We have convection and diffusion. And if we can send a pulse into this reactor, and we can look at the pulse response. But part of the problem here is that we don't have uniformity in the gas phase and the catalyst composition. And then when we send in a pulse of gas, if it's a large pulse of gas, we will consume or release a lot of heat, and that will have its own thermal effects that will have an influence on the transport as well. And so it's going to be very hard in an advecting device to be able to separate in the pulse response itself, in the time dependence, what is actually due to transport and what is due to kinetics. Now, you can take those pulse responses, like I've shown here on the bottom, and you can integrate them and you can calculate conversions and yields, but you can't analyze the time dependence intact because you don't know what is due to transport and what's due to kinetics. And so that's what the TAP method actually addresses, and I'll show that. I'll compare them side by side here. So in the TAP method, we don't have a carrier gas, and we're pulsing a very small quantity of gas, about 10 nanomoles, into vacuum. And so we get rid of convection. Of course, we still have diffusion, but diffusion is what does the efficient mixing for us in the gas phase and for the catalyst as well. Now, this is also going to be an isothermal reactor, because if I'm only pulsing 10 nanomoles, the amount of heat that's released or consumed in transforming those 10 nanomoles is going to be very small. So I can make the measurement isothermally. And then probably one of the best features of the TAP is that the diffusion is well defined. It's just fixed second law, and it can be solved analytically. So when we do a TAP pulse, we know exactly what's due to transport of that time dependence and what of the time dependence is due to kinetics, and we can separate the two. So this is a photograph of the TAP system that we have at Idaho National Lab. We actually have two. It's a fairly rare technique. There are anywhere between 15 and 20 around the world. Sometimes it's hard to keep track of where they're all at and what they're all doing. But it's a very, very simple experiment physically. So the reactor is shown here in the middle with a very thin zone of catalyst. And the reactor is very small. It's about the size of my little finger. And at the top of the reactor, we send in a very small pulse of gas. Again, small for me is about 10 nanomoles. And it's the terminology TAP reactor, I think, is a little bit confusing. It's not essentially intended to be a mini scaled down version of a catalytic reactor. It's really a catalyst characterization tool. And what's different is there's no moving front that comes through the reactor. It's not a plug flow reactor. Essentially, the gas molecules are injected, they spread out through the reactor, and they never encounter each other again. That's what's really fundamentally different about this. They encounter the exit and they escape. They're detected by the mass spectrometer. But in this reactor, the way it's designed, we don't have gas-gas collisions. We only have gas-solid collisions, and they're strictly first order. So this is a far from equilibrium experiment. But what do we want to do with this device? What we want to know, of course, is we want to know the mass action law. We want to know how is the rate dependent on the gas concentrations, but also on the surface, on how it depends on the surface concentrations. And this is very much the realm of density functional theory, where these relationships can be derived from quantum mechanical models. Now, on the opposite end of the spectrum, of course, we've got experimental approach. We can get the rate as it's dependent on the gas phase concentrations using the typical Langmuir-Henshelwood-Haugen-Watson type approach. And we get rate as a function of concentration, but this is a little bit more time consuming because when we're doing a steady state experiment, the gas phase automatically determines what the surface concentrations will be. So I can parse through different steady states and look at the effect of different surface coverages, but that's very, very time consuming because I have to wait for steady state. Now, what TAP does a little bit differently is we're looking at a pulse response. So we get the rate as a function of concentration, and with some more recently developed analytical techniques, we go from the pulse response to this rate concentration dependence. And we see it actually loop around, and it's changing during the experiment. So at one concentration, we may have two different rates. And that's specifically because during the pulse, we're changing the surface concentrations. And so that's one of the benefits of operating at a transient regime, is that you can explore a lot how the rate is dependent on the gas and the surface concentrations as well. So I want to get back to the spectrokinetic reactor, which is what I want to focus on today. So this is what we did. We designed and built a spectrokinetic reactor. It's based on the TAP principles. The publication will be coming soon, but we wanted to have the provisional patent issued. So in this experiment, I want to compare the chromia catalyst reduction and the oxidation. So in the top, I have this device, and I have a oxidized catalyst, and I'm just going to switch on hydrogen and see what happens. And so we see the gas phase response. That's the red trace. So we see the hydrogen pressure come on according to the switch. And then we see the reflection change as well. That's the black trace. And I've gotten them a little bit better. So they're on a similar time scale, but still that reflection changes way too fast. And I really can't understand or analyze it if it changes so fast. And the other thing is I'm in the flow mode here, so I do have those thermal effects. I do see that little dip at the beginning of the experiment. Okay, so it's gotten better, but it's still not exactly what I wanted to do. So now instead I have the oxidized catalyst. It's in vacuum, it's hot, and I'm going to start pulsing hydrogen. Sorry, I'm going to take a drink. Okay. All right, so what we do here is we see the red trace, and that's the hydrogen. It's actually the hydrogen signal, so the hydrogen conversion is 1 minus this signal. So initially, a hydrogen conversion is very high, and I'm making all of this water. And the water is the blue trace, and so initially, high hydrogen conversion, a lot of water formation. And so I think, well, I must be reducing the catalyst because I'm pulling all of this oxygen out as water. Sorry. But in fact, when I look at the reflection, it's not changing at all. And it's not until all of the oxygen is removed as water that I actually see that the catalyst starts to be reduced, right? So the reflection goes up. That's because the chromia 6 centers are being converted to chromia 3 centers. Okay, so this is actually very interesting, because if I had done this, well, doing this in the flow reactor, the switch is so fast, I would not have known that you're required to remove all of this extra oxygen that's not associated with the chromia centers before you actually reduce the catalyst. So this catalyst must be storing some sort of oxygen that is that's being consumed that's not associated with the chromia centers. So I think that's one of the first indications that, okay, we have an interesting technique and we're seeing new things that we wouldn't have seen in a flow reactor. Okay, but let's do this, take this a step further, and sorry, and look at propane. Okay, so we have the same catalyst as before. It's been reduced in hydrogen, and now we're going to flow propane over on the left, and then we're going to pulse propane over on the right. So when we flow propane, we know that we're going to do the PDH reaction, and we expect that we're going to accumulate carbon on the surface, and carbon is, of course, matte black, and so my reflection should decrease, but it doesn't. We see it increase, and so that was a little bit confusing. But recall, you know, in the earlier slide, we showed the thermal effects of heating this catalyst up and how much it changes the spectrum. And so essentially, the PDH reaction here, it's endothermic, and what's happening is when we're flowing the gases, the cooling of the catalyst surface from the endothermic reaction is actually outcompeting the the darkening of the catalyst due to carbon deposition, at least on this time scale it is. So that's, again, one of the confounding effects of doing the flow experiments. Now, if we go on the right and we do the pulsed experiment, where now we have the reduced catalyst, we're pulsing propane, we see what we expect. We just only see this darkening of the catalyst as we pulse by pulse add propane. And of course, we don't have the thermal effects here because we're doing a very low concentration of propane pulses. So the benefit of being able of doing these pulse experiments when you have nanomole quantities of reactants is that the catalyst changes very slowly, and that allows us to study these changes as they evolve. And really the goal here is getting the spectral change and the gas phase measurement on the time scale, on the same time scale, in an isothermal regime, and where we don't have the reactor effects that are obscured by, that obscure the transient data. Okay, so getting to where I wanted to go here. Now I want to get into a little bit more detail. So we have this oxidized catalyst, it's at 560, and we're going to start pulsing propane. And the gas phase information, it's up on the top left. So we see the propane conversion, starts out very high, and then it drops off. And then we see the yield of the different products. So we see CO2 is immediately formed, and we see propylene formation and others. Now, so every single point in the top left, that's the actual conversion and yield calculated from the pulse response itself. But you're not getting the full benefit of TAP if you're just analyzing conversion and yield. So within the pulse response itself, every single pulse response here, we also have that rate and concentration time dependence that we can investigate more closely. And I'm only showing that here for propane pulse response, but we can see how the rate, the gas, and the surface concentration changes pulse by pulse for the reactants and for the products, and hence each point on this is actually an intrinsic rate constant. So we're seeing how these rate constants change as we go throughout the experiment. Now, I'm not going to get into detail on these rate concentration pedals. It's a topic for a whole nother talk, but I just want to point out that really useful kinetic information is there in the data itself. Okay, so going back, looking on the left, we've got very high propane conversion initially, it's oxidized catalyst, and we're just converting all of the propane to CO2. So that's kind of like the gold trace that we see. Okay, so it is a oxidized catalyst, we're pulsing propane, we're making CO2, so we know we're pulling oxygen out of the catalyst. We expect that we should be reducing it. But in fact, when we look at the reflection, we see in this early region where we're only making CO2 that the reflection is flat. So the chromia centers are not changing during that time. So the oxygen that is non-selective, that's making the CO2, is not associated with the chromia centers. So once that is removed, then we start to see the reduction. So the chromia 6 is being converted to 3, and that's exactly when the propylene production kicks in. And so the propylene goes through a maximum, and then after a while we continue to pulse propane, and we're just accumulating carbon on the surface, so the catalyst is just getting darker and darker as we go. Okay, so this is that kind of new information, and I would not have seen this and known that there was this excess oxygen that had to be removed before I could make the propylene. I wouldn't have seen that if I just did the switch, because the change would have happened so fast. Okay, so now I want to do the opposite. So now I've done propane pulsing, I've got carbon on the surface, now I want to turn around and remove it. So same catalyst, different experiment. Now we're at reaction and we're pulsing oxygen. And so oxygen conversion is initially very high, that's the top, and it actually takes a little while for the CO2 to show up and exit the reactor in the gas phase. And now, of course, so I know I'm making CO2, and I know so I must be removing carbon from the surface, so I expect that it will get brighter. But in fact, the first thing it does is the reflection actually drops in this very early regime. So we have to first oxidize the catalyst, and then the carbon is removed. So first the oxidation, we are we're losing chromia 3 centers, making chromia 6. And then that turns around and we're actually removing carbon from the surface, so the catalyst is getting brighter and brighter. So this tells me that the chromia centers have to be oxidized before any carbon will be removed. So this is, it's not the same as the non-selective oxygen that is being used in the PDH. So the key takeaway here is that with this time-dependent spectroscopic technique, we can separate these fast and slow kinetic processes. We can see the oxidation of the catalyst, we can see the oxidation of the carbon, and we're getting these on the same time scale for the transporting of the kinetics. Now, we did one other thing that I want to show you before we move on, and I want to check the time. Okay, so we did this same experiment where we've got a catalyst with carbon on the surface prepared by Clariant. They pulled it directly out of the reactor post-PDH. So there's some amount of carbon on the surface, and instead of pulsing oxygen 16, I'm going to pulse oxygen 18. And so that's some of the data that's shown in the top here. And so when I look at the isotopic signatures, it's clear that oxygen is, the pulse oxygen is mixing with the lattice oxygen because I've got the mixed isotope, and I also have oxygen 32 coming off of the surface when I'm pulsing the oxygen 18. But when I look at the products, the CO and the CO2, I do not see any evidence of the oxygen 18 being picked up. Okay, so all of the catalyst that all of the oxygen that's being used to remove the carbon from the surface, it all comes from the catalyst. It's not coming from the gas phase that I pulse. And we can see that a little bit more detail there. If we look at the pulse response traces, we're not seeing any evidence. So this is the CO2 flux at different times, early, mid, and sort of late in the pulse response experiment. We can see how the kinetics are changing based on the pulse response shape. But we're not really seeing that isotopic oxygen being picked up until much, much later in the experiment. And that's just because of the population. But it's also because of the catalyst, because this catalyst works, removes carbon through the lattice itself. And when we look at the reflection, we see similar to what we saw before. So we have this initial oxidation of the catalyst, and then we burn off the carbon. And then once we burn off the carbon, this reflection at 620, it actually starts decreasing. And we didn't observe that when we pulsed the oxygen 16. But of course, if the chromia D to D transitions are vibronically coupled, then we should expect that the energy is going to change as we increase the population of oxygen 18. And that's shown here. And so essentially what we believe we observe here with this diversion in the 620 reflection is we're observing the rate of oxygen 18 diffusion into the lattice itself. So that's really exciting and a new observation. Now, I'm going to move on to a slightly different topic here. Well, it's the same topic, but another aspect of the data that I hadn't really disclosed before. So, you know, I talked about getting the timescales right of your reactor device and the kinetic process that you want to measure. And something that might have really been easy to overlook and perhaps for me to not even show is if we look at the responses themselves. So I've got two different gas species. So the top is oxygen response and the bottom is the CO2 response. And I'm just looking early and late in the pulse response series. So for the oxygen, this black trace here, this is what the oxygen response looks like very early in the oxidation of the carbon. And it's what we would call a very nice, well-behaved tap pulse response. So there's a transient, the signal goes up, and then it returns to baseline. So we have a fast kinetic component, and then just a nice baseline after that. So that's easy for us to analyze. But what happens as you continue to pulse and pulse and pulse, the response changes and it looks like this. So you have the fast component, but then you have this really, really slow baseline that just kind of slowly comes out of the catalyst. And for people that do tap experiments, this kind of response is really a pain in the butt because it's hard to analyze. But what it's telling me is that what might not be surprising, as the catalyst is oxidized, it's slowly releasing that oxygen back into vacuum. And so that has to be taken into account. So I have two kinetic processes here that are being represented. And let me just describe the CO2 before I get too far. Now the CO2 does the opposite. So CO2 being formed early in the oxidation is I would say poorly behaved, because we have this fast transient and then this very slow release of CO2. But then as the catalyst is more oxidized, it gets better behaved, and we just have a pulse response that we can easily analyze. And so the shading that I've done here, the green and the blue, are just representing the two different portions of the peak that are the fast kinetic component and the slow kinetic component. And so we can analyze those separately, and that's what's shown in the center, the fast versus the slow. And we see they change differently. So they're different kinetic processes. But the point that I want to make here is that even this baseline in the tap pulse response has very valuable information. And in fact, most of the CO2 is being made in that slow kinetic process. But it's a problem for the tap experiment in and of itself, because this process is too slow to be measured in the device on the time scale of the pulse response itself. Okay, so what can we do then? So we can design the experiment a little bit differently. And what I'm going to do here is I'm going to rapidly pulse oxygen. So again, I've got a chromia catalyst. It's got carbon on the surface, and I just want to understand the kinetics of removing that oxygen. So in the green area, I'm going to rapidly pulse oxygen, about 50 pulses of oxygen. I want to oxidize the catalyst, and I see the CO2 being formed. That's the black trace. And I see the reflection is dropping because I'm losing the chromia 3 centers to chromia 6 centers. And then after I pulse all this oxygen, I kind of fill up the catalyst with oxygen. I'm just going to stop pulsing, and I'm just going to watch and see what happens as it sits in vacuum at this high temperature. And so that's the blue area. And what we see is that the CO2 continues to come off the surface because the oxygen in the catalyst is continuing to reduce is continuing to oxidize or remove that carbon from the surface. So that's black trace. The CO2 continues to come out. And then I also see the reflection increases because of that reduction process that's taking place on the surface. So that's the red trace that increases here. And the one thing that we'll note from this is that these rates of the chromia reduction and the CO2 formation, they're not the same. Okay, so we'll continue to do this many cycles of rapidly pulsing oxygen and then holding it in vacuum and watching the CO2 formation and the reflection change. And that's what's shown here. You can see over many cycles of this. Okay, I'm wrapping up. You see the reflection going back and forth, and then over the long experiment, the catalyst gradually becomes oxidized. Now, the oxygen conversion itself, that's over here on the right, that conversion drops. This is the signal. Conversion is 1 minus that signal. Conversion drops, but one thing we notice is the CO2 production, it's generally the same. It's not really changing even as we oxidize the catalyst itself. So let's look at what one of these cycles looks like later in the process. So here, this is the 11th cycle that I'm showing here. And now the oxygen conversion has decreased, but it's still pretty high here. And the CO2 formation is very much the same. So CO2 formation is shown here in black, and I haven't changed the scales from what I showed you earlier. But what I notice is that the reflection is no longer changing, okay? So I'm still making all of the CO2, but now I am not making CO2 with oxygen that's associated with the metal centers. So that's very interesting, because this is one of the very first points that I brought up. If you recall this experiment here, we're reducing an oxidized catalyst. So we have oxidized catalyst, we're pulsing propane. And remember, we saw this initial period where we removed this excess oxygen that's not associated with the chromia centers. Now I'm doing sort of the opposite experiment. I have a reduced catalyst, and I'm oxidizing it. And by the time it gets oxidized, I'm not making the CO2 with oxygen associated with the chromia centers. So in these two different experiments, we're measuring the same non-selective oxygen that's working with two different reactants. One is working with gas phase propane, and the other is working with a surface carbon. Okay, so this is exciting and new observation. And this is really where like the tap characterization technique comes in, because being able to make these measurements, and although I haven't actually done it in this presentation, to be able to compare different catalysts and say, you know, why does this catalyst work better in the process than other similar compositions? Now I can start to compare them based on, well, how much of this non-selective oxygen is there, and what are the kinetics of this fast versus slow oxygen consumption. So that's really the sort of the direction that one wants to go in characterizing catalysts using this method. So just kind of want to recap real quickly. The importance of doing operando transient experiments is getting the kinetic and spectral response on the same time scale. And I showed that pulse to pulse on seconds, and then looking at the multi-pulse series, which takes place over hours, and then this sort of rapid pulsing and relaxation on this time scale of minutes. But what about looking at the spectral response changing during the pulse? This is something that I've wanted to do for probably 20 years. And so I'm going to show you a very, very new result that we don't entirely understand, so I hope that you'll forgive me. And I'm wrapping up very quickly. So this is the data over here that I've shown. Everything has been UV vis here to now. And I'm going to do the experiment a little bit differently, because we couldn't quite get the time resolution that we wanted. So instead of showing this broad band of light on the catalyst and looking at all the reflections, I'm just going to do a photoluminescence experiment. I'm going to shine 532 coherent light, and then I'm going to look at the photoluminescing from the chromia 3 centers. So the experiment is pretty much the same. I have an oxidized catalyst. I'm pulsing propane. The gas phase data is essentially the same. It should be. It shouldn't have changed. And the spectral response for the UV vis and the photoluminescence experiments are very similar. We have this initial combustion period where we're combusting the propane. We reduce the catalyst centers and we start making propylene, and then we have the carbon deposition. But what is really exciting that you can't see here is that we've actually resolved all of the time dependence within this experiment. So I'll quickly wrap this up. Now, what's shown here is a time resolution of 50 milliseconds. We believe we can do 1 millisecond. We're just waiting for faster detectors to arrive. And I'm going to skip over this because what's really exciting is here, if we zoom in on the different pulse response in the different chemical regimes, we see that the shape of the photoluminescence response is changing. So it's clearly an indication of the chemistry that's going on. And in this region where we're making all the propylene, in the PDH region, it's a very long-lived photoluminescence response. So it's much longer surface relaxation process than earlier where we have the combustion period and where we are just accumulating carbon. But I want to really emphasize the importance of this and what it's taken to actually get the red trace, which is the photoluminescence response, on the same time scale as the gas pulse response in these TAP experiments. So that for me is very exciting to be able to see those all together, to see the gas phase changing and the surface changing in response to the pulse. Now, okay, I think I'm out of time. Yes. Okay. I could talk about why we think this lifetime is getting longer and what we think is happening there, but again, it's pretty new data and it's really exciting stuff. So I won't read the conclusions here, but I think the key point that I want everyone to take away is that operando experiments are great, but to do transient operando experiments are very challenging. And I think that we've shown some really exciting results using this new reactor device that's based on the TAP principles to be able to observe the gas phase and the surface changing on the same time scale. All right, thank you very much for your attention.